Okay, so now let us come to Bernoulli's theorem. Bernoulli's theorem in fluid mechanics is the work energy theorem of mechanics. Now you see the basic idea of even work energy theorem is Newton's law. At the root of every work energy theorem we have Newton's law. Similarly, when we apply the laws of motion to a fluid particle, we can also get to the work energy theorem of the fluid particle, that is called the Bernoulli's theorem. So we will see the energy conservation principle later on. Presently let us see the motion of fluid particle along a streamline and how such an equation can predict the Bernoulli's theorem. So what I am going to do, I am taking a streamline like this, and we have a fluid particle. Now this time I will take the fluid particle as a cylindrical element. My fluid particle is having a cylindrical element and it is moving down. So the streamline is, the direction of the streamline tells that the velocity of the fluid particle is here. So now you see, let us see the forces acting on the streamline, on the fluid particle. So the force acting here is pressure P into dA, where dA is the area. Now as I go this, the pressure changes to P plus dP into the area dA, and let this length be ds. So the fluid particle moves and it comes down. You see, this is the differential element. This length ds is denoted here and this becomes dz, and this is the datum and this is at a height z. So the gravity is acting downwards, the vertical, and so z direction is the vertical direction. So now let us see what. So consider a fluid particle in the form of cylindrical element along the streamline shown. Now let us see what are the forces. These two forces, and there is another force that is acting downward, that is dmg. So we have three forces. There can be another force that will act against the direction of velocity, that are viscous flow. So applying Newton's law to the fluid element. So in bracket we neglect viscous forces, i.e. the flow is inviscid. So what are the equations? So the total force downward is dmg plus pda minus p plus dp into dA is equal to mass. Mass is rho ds into dA g into the acceleration dv by dt. So you see this p term and pda will cancel out. This mass is again here rho ds into dA, rho ds into dAg minus dp into dA is equal to rho ds into dAg, and we have dv by dt. So you see here dA cancels, and you see no here mass, so g is not there, so only mass here, mass into acceleration. So this is the Newton's law. Now when we want to include friction force we have to include friction force here, and so the equations will change. So that means present one assumption is that the flow is inviscid. So the following, so the result is valid only for non-viscous flow. Now let us bring this ds here, everywhere rho ds, or let it be here. So let us simplify it, rho ds g. Now one more thing, I have missed one. This weight is acting in this, so I will have not here this but dmg sin theta. So here one sin theta will be there. So here dmg sin theta. So here rho ds dag sin theta. So sin theta, one more term will be there because the force is dmg is downward, it is dmg sin theta. So now you see here, this is dp and this is rho ds into dv by dt. So we have where we should be very careful with the components. So this is equation number 1. We want now dv by dt. So what we do, in order to calculate dv by dt, I have to use result of partial derivative. So from partial derivative dv is equal to dou v by dou s into ds plus dou v by dou t into dt. I want dv by dt, so I have dv by dt will be equal to dou v by dou s into ds by dt plus dou v by dou t. Now I have to substitute this dv by dt at this place. Now I assume that now since the flow is steady, so dou v by dou t is equal to 0 and dv by dt finally get replaced only by dou v by dou s into ds by dt, which itself is v. So now I have to replace this only here. So now let us replace it. So we have rho ds g sin theta minus dp is equal to rho ds into dv by dt, that is v dou v by dou s. Now you can see this term can be further simplified, and also you can simplify this term. I have this angle as theta, the angle this, so ds sin theta is dz. Since z is measured here and it is coming down, so I will write minus dz. So this ds sin theta is minus dz, so I will write rho g dz minus dp is rho. This can be written as rho by 2 d of v square. So let us see how it can be written. If I have to write dou v dv square, I will write this is dou v square by dou s into ds. This is further can be 2v dou v by dou s into ds. So you see this is ds v dv by ds, ds v dv by ds, that is dv square by 2, what we have written. Further simplification gives, let us bring all this at one place, rho by 2 of dv square plus dp plus rho g dz is equal to 0. Now one more condition, if I assume, now if rho is constant rho is constant, then rho can come under this differential, then we will have d of rho v square by 2 plus d of p, and d comes here rho gz is equal to 0, implies rho v square by 2 plus p plus rho gz is equal to constant along the streamline. This is Bernoulli's theorem. This is Bernoulli's theorem. So this is called Bernoulli's theorem. Now according to Bernoulli, along a streamline, this p plus rho v square by 2 plus rho gz remains constant if, let us see what are the conditions. If number one condition, the flow is inviscid, that is non-viscous flow. Second, the flow is steady, dou v by dou t. You can see again rho is constant, incompressible flow. So just recall, Bernoulli's theorem tells that if in a inviscid flow, number one condition, inviscid flow, non-viscous flow. Second, steady flow, that is streamlined flow. And third, the incompressible flow. So in a non-viscous, steady flow, incompressible flow, rho v square by 2 plus p plus rho gz remains constant. This is what Bernoulli's theorem. So we have seen that all these limiting conditions we are imposing on the fluid particle comes from where? Now suppose I want that I require my flow to be compressible. That means here I have to work from this part, not from here, because here I have assumed rho constant, then only this is constant. So in that case we will use from here. Some modifications will be required. Now if I want my flow should be for steady, unsteady also, then I have to take this whole term in place of dv by dt. Not only, we can't take this is equal to 0. Next, if I want my flow to be viscous also, so again here I have to take the surface, the viscous forces also. That means in this derivation we have seen that the general principle of Bernoulli is valid only for viscous, non-viscous flow, incompressible flow and steady flow. And we have also learned that if I don't take these assumptions, then how the equations will get modified. So now we have seen the Bernoulli's theorem, that was p plus rho v square by 2 plus rho gz remains constant under the three conditions, that is the inviscid, incompressible and steady flow. So this is called the work energy theorem of fluid. So in order to discuss further or derive the result from the law of conservation, let us first define the kinetic energy, the gravitational potential energy and the pressure energy of a fluid. So let us see first the kinetic energy per unit volume of a fluid. So let us define the kinetic energy per unit volume. So this is simple expression, the kinetic energy K per unit volume will be, kinetic energy is half mv square upon this volume is V, it may not be confused with this. So divided by volume. This mass will be density into the volume of the liquid by volume. So that is rho v square by 2. So that is kinetic energy per unit volume of a fluid is given by rho v square by 2. So this is the kinetic energy per unit volume. Now then gravitational potential energy per unit volume, let us calculate. So that is gravitational potential energy per unit volume of a fluid. So let us define this term, kinetic energy as Ke, and this is Pe by volume, this volume. So we call it, for Pe the letter we reserved is U, and for volume like this. Suppose M is the mass, then mgh will be the gravitational potential energy, V is the volume, then mass rho into volume V into G into H, that is V. So V cancels, so rho GH. So H or Z, anything V you can use. Thus the expression for gravitational potential energy per unit volume is equal to rho g, h or z, anything we can use. So apart from kinetic energy and gravitational potential energy, a fluid can possess third energy that comes from its pressure. So a general material particle, so you see material particle possess two energy, kinetic energy and potential energy. But a fluid element contains three energy, kinetic energy, this potential energy, that potential is gravitational potential, and then pressure energy. So we have three energies for this, but for a material particle it is only two energies. So let us see the third, that is pressure energy per unit volume. So now the pressure energy per unit volume. Let us come to the origin of this energy. So what is first kinetic energy? The energy possessed due to the motion of a body is called kinetic energy. Next, gravitational potential energy, the energy possessed because of the height of a fluid. So how much head the fluid is having. So you see, more the height of the liquid, more energy it will possess because of its gravitational potential energy. Next, the third energy is its pressure energy. So you see, suppose a compressed gas is there inside a vessel, and the vessel suppose breaks, then the gases come out, and the vessels, the pieces of the boundary wall flies in all directions, and thus they acquire some energy. So all these energy is actually stored inside it in the pressure energy form. So let us calculate what is the pressure energy per unit volume of a liquid. So now consider a liquid which is inside a vessel. So this is a vessel, and here inside this vessel we have a liquid, and this height is h, and suppose here the liquid pressure is P. So, and this is a piston. So with the help of this pump we are inserting liquid from this. So we are pumping liquid inside this. So what happens, we have a liquid outside, and when we pump inside, the liquid comes under a pressure. So you can see the reverse. If a liquid is allowed to come, it comes and it can do some work. So the work done by the liquid is because initially it has some energy. You see, the liquid is at the same height. So where there's this liquid, the energy comes. So because the liquid is under a pressure and suddenly the pressure is released, so the kinetic energy it acquires is because of this pressure. So let us see the reverse, that if we are pumping liquid from outside, that means we have to do certain work and that work is stored here as a pressure. So let the work done by the external agency to pump dm mass of liquid at the bottom of a vessel B dW. So you see, dW is PdV according to the expression we have derived in thermodynamics, the hydrostatic work done. This is called the hydrostatic work done. So the hydrostatic work done dW is equal to PdV, and dW by dV, this dV is the change in volume, is equal to P. This work done, this hydrostatic work done, static work done is stored in the liquid as pressure energy. So you see, the work done per unit volume comes out to PP. Thus the pressure energy of a fluid per unit volume is its pressure itself. So now I have defined the three different forms of energy which a fluid can possess. So now I can work on the work energy theorem, that is the law of conservation of energy for fluid. And now let us derive the Bernoulli's theorem in terms of energy. So now let us consider a fluid flow. So we will assume this as our datum. Datum means reference line. That means all distances are measured with this. So the potential energy at this datum is assumed to be 0. So let us consider a tube of flow. So this is a tube of flow. So now you see here, this tube of flow, that is a bundle of streamlines is there. That means what I said, that the fluid particles move along a streamline. That means in order to describe a flow, I have to use a bundle of streamlines. That is a tube of flow. And here at a height of Z1, this bundle has a height H1. This is neglected, or you can assume that this is small, or you can take the average. Z1 and Z2 is this heights of the flow. Now, so we consider a fluid flow and this cross section is here. That means we see this fluid within this boundary, this one. So you see here A1, A2, B1, B2. So the liquid is initially at the cross section A1, A2 to B1, B2 at T time, and next it comes to this dotted position after certain time and to this dotted position another time. So this is at one time this liquid, and the same liquid is transported to this position. So this line A1, A2 is the position initially, and suppose I say it is B1, B2. So after t time, dt time, this has moved to this position and this has moved to this position. So now let us assume that here the average velocity is V1 and the average velocity, so average means average over the space is V2. So V1 and V2, so that if there is a small difference, then that can be compensated. So this is average velocity, average over the space is V1 and V2. Here area of cross section is A1 and here A2. So A1, A2 is the area of cross sections, or we can assume S1, S2 also area of cross section. Now here the fluid is applying a pressure P1 and here the fluid pressure is P2. So this is the standard symbols, pressures at here P1 and P2. So consider the flow, the steady flow, steady incompressible and inviscid flow of a fluid of density rho as shown in figure. So in figure, the tube of flow is shown in figure. So let us assume the standard symbols, V1 the velocity at this position, V2 there, P1 here, P2 pressures there, Z1 height, Z2 there. So now we are interested in using work energy theorem. So according to work energy theorem, change in work is delta K. That is, the work done is equal to change in kinetic energy of the system. Here work done, there are different types of forces here. You see gravity is there, then pressure is there, and there may be some dissipative work done. So in the absence of dissipative forces, only gravity and pressure does work. So only pressure energy is doing work. So you see the work done by pressure energy is P1 and into the change in volume. Suppose here the area is S1, area of cross section is S1. So the work done is P dV. Let us write as dV. dV is S1 into time T1 dt. So P pressure into change in volume. Let us write as P1 into delta V1. This is the work done here. And there you see the pressure is acting and volume is here. There minus P2 into delta V2. So this is the work done by pressure plus work done by gravity. You see gravity is down and you are going up. So work done by gravity is how much? So minus mg is acting. So mg is acting downward. So it's minus into Z2 minus Z1. And that is equal to, so this is the work done by pressure force. This is the work done by gravity force, where m is the mass of the liquid which is moved from here to here. That is equal to change in the kinetic energy. So this mass and this mass is the same mass, cannot be created, that we can see from continuity equation. So half, suppose I say that this mass is m, let it be m, then it will be V2 square minus half m V1 square. So let us see about mass. So you see this mass is rho into the volume it changed. So how much volume? the mass moved in dt time, so the mass will be rho v1 dt. So in dt time suppose it moves, so rho v1 dt is the length into ds. So this is equal to mass. This mass is equal to this. Now we know that this is area. Area I have assumed to be S1. So now you see here, this can also be written as, you see, V1 S1 is equal to V2 S2. V2 S2 rho dt. You see, V2 S2 is equal to V1 S2 from continuity equation, and so this is equal to this we can say, and so later better it to write it as M, so that M can be easily cancelled out. So you can see from continuity equation S1 V1 is equal to S2 V2. S2 V2 and S1 V1 is here. Simply rho dt if you will multiply, you will get mass, and mass is the same for here. The same mass is transported here. Same mass we are considering. Now you see pressure into delta V. Delta V means the here whatever this pressure into delta V means the volume occupied by this mass. So volume occupied by this mass I can write as this delta V1 is mass is equal to mass by rho, minus I can again write this is mass by rho, minus mg z2 minus z1 is equal to m by 2 common v2 square minus v1 square. So now m can be cancelled. So I will write P1 minus P2, then again I will multiply by rho g z2 minus z1 is equal to, this rho is cancelled out, rho by 2 v2 square minus v1 square. Let us arrange this in one side one term, another side another term. So P1 plus, this is z1 means minus, so plus rho g z1 plus this v1 term here rho v1 square by 2 is equal to P2 this side plus rho gz minus, so it will become rho gz2 plus this rho by 2 v2 square. So what I got, that this term at position 1 and this term at position 2 is the same. What is this term? The pressure energy per unit volume, the potential energy per unit volume, the kinetic energy per unit volume remains constant. What is this theorem? That is the work energy theorem for the conservative force, because there is no viscous drag here, no dissipative force. Thus Bernoulli's theorem is nothing but the same law of conservation of energy applied for a fluid flow. Thus what we arrived, thus Bernoulli's theorem is the law of conservation of energy, for a fluid flow. So what is the statement? According to Bernoulli's theorem, the sum of kinetic energy per unit volume, pressure energy per unit volume, and the gravitational potential energy per unit volume in a steady steady. Number 1, incompressible. Number 2, and inviscid flow remains the same. So we write P plus rho g z1 plus rho v1 square by 2 is equal to P2 plus rho g z2 plus rho v2 square by 2. That means pressure plus rho g z plus rho v square by 2 is constant. This is what Bernoulli's theorem is.